everyone. Okay, so in the previous lecture we have introduced what's known as a PN junction diode, and specifically we have looked at what are called semiconductor physics. We have looked at how to construct a hypothetical PN junction diode, and then we looked at the electrical characteristics of the PN junction diode, and we've seen how to model such diodes, which is more simpler than the practical ones. The application would look at in this lecture, and we'll also do some examples. But let's simply summarize what we have done in the previous lecture. Okay, so the first part is how to construct such semiconductor materials. So the basic starting point is to look at the periodic table and then get one particular element which is most common. This is a silicon, so this is a group 4 element. But this is not the only one. For example, one may also use germanium, because both are on the same blocks or on the same columns. Either way, suppose you construct, suppose we have produced some sort of a block of a silicon lattice that consists of, let's look at it this way. Suppose one wants to construct a diode. The first part, of course, is to sort of get two parts. So the first part, you start with a silicon lattice. The second part, you will also start with a silicon lattice. So if you actually look at the arrangement of such atoms, everything is paired with the valence electrons of 4. So that's the starting point. So this is a pure silicon lattice. If we add elements from either side of group 4 of the periodic table, which means if one goes to group 5, pick an element, and one group 3, and pick an element and add to such a lattice, then that process is called the doping, or in other words, addition of impurities. So let's look at the silicon lattice, but in this case now impurities will be added. So the same lattice where we have of pure silicon elements or silicon atoms was as such, and we add impurities. So let's simply say there is a hypothetical division at this point. In a practical sense, one will actually start with what are normally called wafers, pure silicon wafers, and then you add impurities. So if you actually look at the impurities that we add in this case, to the left side we have one element which has the valence electrons of 5, and compared to the silicon atoms it has one more electron. On the right side, let's introduce an element to this lattice. This has a valence electrons of 3, and compared to our silicon element it has a deficiency, or it contains one less electron. So this is a very simple example which only shows the addition of one impurity from group 5 and addition of one impurity from group 3 to our silicon lattice. So by doing such a process, we say that this process is called doping the silicon lattice. So if you actually look at the arrangement of the atoms, the addition of an element with extra one electron compared to the silicon element introduces or creates one extra electron which wanders around such a lattice. Similarly, on the other side, since we have introduced an element which contains one less electron than the silicon atom, it creates a very unique condition which consists, or which is depicted as containing one less electron. Now the question is, what do you say when one less electron is present in a lattice? So in either case, we have a deficiency. So in other words, this place or this position can accept one electron. In other words, so there's a deficiency of one electron. So we have one type of material on the left side, and we have another type of material on the right side. So this is normally what are termed as the PN, but in this case that will be the NP type of semiconductor. Okay, so in this case what we have done essentially is that we have added impurities to the pure silicon lattice, and by doing so, on the left side we have created one free electron, and on the right side we have created a position which can accept such an electron, also the deficiency of electron. Okay, so this is a basic starting point, hypothetical of course. Then we call such a structure a PN junction. So the junction actually comes from this part because you enjoined two elements. One part is a P and the other part is the N. Okay, so since we actually do not want to talk in terms of lattices, then one would actually go to get some sort of a block diagram representation of the previous process, and by doing so the previous process can be represented quite effectively. So what we have done is that from the previous side we have, if you look at, okay, things might get a bit reversed in a sense that in the previous slide that was an NP, but in this case we have a PN, but the same process applies. So at the junction side we have okay, so the N-type semiconductor creates free electrons, and the P-type conductor creates the deficiency of electrons. And let's simply insert some metallic material, piece of wire that connects to the P-type. Similarly, let's add some sort of wire to the N-type. So by doing so, essentially we have the PN-type semiconductor, so which essentially is a diode. So if you actually look at it, there is an electric field barrier between the P-type and the N-type. So in other words, there is some sort of a barrier between these two junctions. So to overcome such a barrier, one needs to construct a circuit for this type that would overcome such a barrier. Okay, so our next point is what's called the electrical symbol. Then how do you depict such element? And then we have seen that to depict that element we use some sort of an inverted triangle, or triangle on the sideways. These are piece of elements that correspond to the previous case, so we call this a diode. Normally the electric field barrier, depending on the model, can be remodeled into such an equation, into this graph. So by itself the device is not of much use. So to make such a device useful, then one needs to construct circuit around it. So in other words, for example, if we add some sort of a potential or power supply, so let's assume that this is a power supply. Let's connect it to the diode. Since it's always a good idea to sort of put a resistor always to limit the current so that one might not blow up the diode. So this is normally called a current limiting resistor or simply a resistor. We have a power supply, and by doing so we can actually put current into this diode. One can actually try to measure the voltage between these 2 points. Okay, so what happens in practice is the diode shows some sort of electrical characteristics which is quite unique in the sense that it does not obey Ohm's law. So our next discussion that last week was to look at the electrical characteristics of such a diode under such conditions. Okay, so what we have seen is that the electrical characteristics of this diode, ID versus VD, which means the current and the voltage through the diode, is as follows. And then we have divided or looked at such a diagram into three ways. The first part deals as such. Second part, or the second region, is this part, and the third region is this part. We'll explain what this really means just now. Okay, so the first part, which is on the positive, when you apply positive voltage, essentially, the diode does not actually do much, which means if you actually look at it, the current is 0, which means our diode is an open circuit. But something unique happens at about 0.6, which means when the voltage approaches and exceeds 0.6, then the current shoots up, indicating that current flows. So the 0.6 volts is normally called the threshold voltage, and it depends on what element is chosen to construct the PN junction diode. In most cases, the silicon element is considered. That's about 0.6 to about 0.7 volts. Other constructions involve a germanium atom, which has a lower threshold voltage of 0.2. But in either case, that threshold voltage must be overcome for the diode to be considered a short circuit. Okay, so the first part of the characteristics is really nothing happens, the diode is off, and once you exceed the threshold voltage, then the diode conducts. So this type of behavior is normally called, that's the forward bias. So you actually bias, or you put positive voltage to the diode. So we have a forward bias at this point. The second region is the reverse bias. So when you do reverse bias, essentially what's actually been done is that you reverse the polarities of the voltage, or in other words, instead of applying positive volt in this power supply, you apply negative volt. So when you apply negative voltage, essentially you can measure a very small, minute amount of current in the range of, if you actually look at it, as -1 nanoamperes, which is extremely small and of not much good use for any real practical application. So technically we can assume that that's a 0. So that's the reverse bias, the diode is off. But if you continue to increase the negative voltage, then there is such a point, let's say in this case -100 volts, after which the diode will start to conduct again. So there are three regions for such a diode, which is the forward bias, the reverse bias, and the reverse breakdown bias, or the reverse breakdown region. Okay, so that's the electrical characteristics of an actual practical diode. And in most cases, for most electronic circuits, then the voltage is limited at most to about from -12 volts to +12 volts. Then we will consider mostly such a figure, which is the forward bias and the reverse bias. So if you actually look at most applications for diodes, the forward and the reverse regions suffice for practical uses. Okay, next thing we looked at is, okay, we've looked at our previous electrical characteristics, but it seems to consist of many non-linear curves. So one way to actually avoid such curves is if we assume that our diode is ideal. So what does an ideal diode mean? So for an ideal diode, there is no threshold voltage. So 0.6 is in fact 0. Under that conditions, then this curve will actually come at this point. The next, there is no reverse breakdown region. So essentially the characteristics, or the electrical characteristics of the diode, is very simplified, or it's very simple. Essentially, if the voltage is less than, voltage applied to the diode is less than 0 volts, then the diode conducts, the diode is off. If it is larger than 0 volts, then the diode conducts. So such a model is called an ideal diode model. Another diode model which is important is closer to the ideal diode model is now, in this case we'll consider the offset or the threshold voltage of the diode. So in such cases we'll still consider the threshold at 0.6, but we do not assume any nonlinearities. So if you actually look at this curve, it's actually modeled by 0 as such. To the left of the diode, that will be very similar to the ideal diode model. So such type of modeling is called an offset diode model. The only difference between the offset diode model and the ideal diode model is that we consider the threshold volts at this point. We'll look at, by way of examples, we'll look at the effect of the offset diode model compared to the ideal diode model. So I think that sort of simplifies or covers what we have done on the previous lectures. So for today, let's look at this example. Okay, so the example states, for the following circuit, assume the diodes are ideal. So which means we can use the ideal diode model to represent this diode. So in other words, the threshold voltage of each of these diodes is 0 volts. So find the state of the diodes, which is another way of asking which diode is on and which diode is off. And the circuit configuration is as shown. It's taken from the textbook. So you have 10 volts as a power source connected to 4 kilo ohms, connected to such a diode, and then connect to the 6 kilo ohm resistor. On the right side we have the diode in such a direction, and it's also powered by 3 volt power supply. So the question is, which diode is on? Is diode 1 on? Is diode 2 on? Is one of them on, one of them off? Or are they all off, or are they all on? So the total conditions that we can have is, the first case, both diodes are off. So D1 is off and D2 is off. Second case is, let's assume that D1 is on but the second diode is off. Third case, let's assume D1 is off and D2 is on. And the fourth case, D1 is on, D2 is on, which means both are on. So for each of these cases, because these are all the valid conditions, and there's only one valid answer. Okay, so the point is, how do you pick that valid answer? Okay, so to pick that, or to validate each of these points, we need to assess the effect of such an assumption on the circuit. So let's do it one by one, and then we'll see what will happen. So let's look at the case where D1 is off and D2 is off. So in that case, if you actually look at our diode circuit, let's try to get the equivalent circuit of, okay, so let's say that we have a resistor, or we had a resistor at this point, and then we have this diode position where it's considered to be off, and then let's say we have this point, which is another resistor, and we had in place of a diode at this point, and then let's also have this part. Okay, something like so. Okay, so let's simply assume that at this point this was 10 volts, and let's assume that this was, I think, given as 3 volts, and then we have a resistor which is, let me look at it, that's 4 kilo ohms and that's 6 kilo ohms. So we have 4 there, we have 6 there. So this is where diode 1 was, and this is where diode 2 was. Okay, so this is the equivalent circuit of such an assumption. So the point is this a valid assumption? So to validate that, we need to test each of these. So let's test D1 whether it's really off. So to do that, Then the one thing to ask is what will be the voltage at this point. The voltage at this point is connected to 10 volts and there is no complete circuit at this point. So one can assume that the voltage is at this point is 10 volts. Okay, and the next question is what is the volts at this point? Okay, so if you actually look at this point, it's connected to the resistor, which is connected to 0 volts, because mind you that this point, which is a ground point, is normally 0 volts. So the point that we have there is 0 volts. So if this is 0 volts, it's connected to a resistor and both sides are open circuits, so necessarily at this point we also have 0 volts. Okay, let's say this is 0 volts. Now the question is, for a diode, if at one end we have 10 volts and at the other end we have 0 volts, and the polarities of the diode is such that it's forward biased, in other words, with such a diode was, this is the diode. So for this diode, if you apply 10 volts at this side and 0 volts at this side, then the question is, would it conduct or would it not conduct? So if you look at the electrical characteristics, that will be the forward bias region, then the diode should conduct or is expected to conduct. But our assumption states that the diode is off. So that's an incorrect assumption. At least at this point, the diode should have been on, but our assumption says the diode is off. So this is this is a true statement. So if connected by end, so for true statement, if any one of the statements is false, then the complete statement is false. So if any one of the sub-statements is false, then the complete statement is false. So case 1 is not a valid assumption. But that being the case, let's also try to see what happens at diode 2. So for diode 2, then the diode 2, the setup was as such, or the original diode was placed as such, and we assume that it's off. So at this point, then if you look at it, what will be the voltage at this point? Then that 3 volts connected straight to the 3 volt supply, and at this point that's 0 volts. So even if this is the case, then 3 volts at this point, and we have at this point 0 volts, and then the electrical characteristics would tell you that this diode is in the forward bias and it should have been on. So D2 is off. So there's something wrong about such a statement, which is completely invalid in either ways. Okay, then let's look at the second assumption, which is that D1 is on and D2 is off. So let's try to quickly write such okay, so our circuit looks like something like so. I think that those are the same circuit as before, but in this case D1 is on. So maybe let's try this is a connection at this point, so these 2 points, maybe let's assume that our D1 now is connected by a piece of wire. D1 is on, but the D2 assumption states that it is off. Okay, so D2 is off. So let's try to validate such a statement. This point is 4 kilo ohms and 6 kilo ohms. Okay, so 4 kilo ohms and 6 kilo ohms. So let's say that this is 4K, and let's say that this is 6 kilo ohms. Just to, we might need it to calculate it. Okay, so let's check the first assumption, which means let's validate whether D1 is on. If D1 is on, or if the circuit is as indicated, then it means that positive current flows through this diode. So which means one might expect a positive current to flow through such current. Okay, so the point is now what will be I. So that to get I might not be much easier if you write on the PC, but in either case we have 10 volts, then you divide by 4 kilo ohm plus 6. Okay, so if you actually compute it, that will be 10 divided by 10, then that will be 1 milliamperes. So in other words, the current of 1 milliamperes flows through such a case, through such a circuit. Okay, so if, or in such a direction. So the question is that a valid thing? Okay, so let's see where our diode position is. Okay, so if the diode was in such a direction, then what current would one expect to flow in such a direction? So then one would expect a positive current to flow in such a direction. So this is a forward bias circuit. There is no threshold voltage of the diode. Then a current of 1 milliamperes actually passes through the circuit. So that's one way to test it. And then let's go. So D1 is on, is a valid assumption because a positive current flows through it. Let's test the second assumption, which is D2 is off. So if D2 is off, then we'll try to test such an assumption. D2 is off. Okay, so to test this assumption, we need few points. So one thing that we need is that the voltage at this point, which is 3 volts, but we also need to know the voltage at this point. The voltage at this point is actually equal to the voltage at this point. And what will be the value of this voltage? Okay, so we need to get such a point. So to get this point, we know the current, which means this current is 1 milliamperes. That will be the same current that flows through the 6 kilo ohm resistor, because at this point there is an open circuit. So to get the voltage drop in such a resistor, that will be 1 milliamperes multiplied by 6 kilo ohms, and then one would actually get 6 volts. Okay, so we have 6 volts at this point, which means we have 6 volts at this point, and we have 3 volts on the other side. In other words, what we're trying to say is that at this point we have 6 volts, and at this point we have 3 volts. So this arrangement cannot be forward biased, it's a reverse biased, because the voltage on the other side is higher than the voltage at this point. So this reverse side can or has to be modeled as off, or the diode is off. So such an assumption is a valid because this is a true statement connected by AND, and then we have verified both statements as correct statements, which makes the complete statement a correct or true statement. Okay, so that's case B. D1 is on and D2 is off. Okay, so if a diode conducts, to summarize, if a diode conducts, then a positive current should flow through it. If the diode is off, then the voltage at the anode and the cathode must be according to the reverse region or reverse bias setup, and this satisfies both such setups. The first one is forward biased and the positive current flows. The second case is the reverse bias and the voltage is higher than the one that you will get at this point. Okay, so let's look at the third assumption, which is D1 is off and D2 is on. Okay, so let's look at such a case. So I've just quickly plotted this, and D1 is off, so we would leave D1 the way it is, and D2 is on. So let's use a piece of wire to connect where D2 is. Okay, so that we do not forget the setup for each of these diodes. Okay, so this is where D1 was. So if this diode is modeled or assumed to be on, then it must satisfy conditions of forward bias, and D1 is off. So if D1 is off, then it must also satisfy conditions of reverse bias, because that's the only case where we could have an off diode. Okay, so this is what the information that's given to us. Our job, of course, is to validate this too. So let's validate the first statement. D1 is off. So if D1 is off, and if the diode is in such a setup, then it must be on the reverse side. If this is on the reverse side, if such the reverse side, let's call this text. Let's call this V1. Let's call this voltage 2. Then the setup is, if this is going to be reverse biased, then the assumption is that V2, or the voltage at this side, must be larger than V1. Thereby you make it reverse side and it's off. If this diode is going to be on, then a positive current should flow through it, or the voltage should be larger. Okay, so let's try to get to that point. So this is 10 volts, and then we have 10 volts at this point. So our V1 is in fact 10 volts. The reason is, since this is an off or is not connected, no current flows, so this 4 kilo ohm resistor, there is no voltage drop, thereby making the voltage V1, which is equal to 10 volts. Then the next point, we might need to calculate this current I on the other part of the circuit, in fact, because that part is connected. So what will be the current I? Then if you can actually quickly, in fact we actually do not even need to compute the current I. So this is 3 volts. So if this is 3 volts and then the diode is connected, then the voltage at this point is in fact 3 volts. Okay, so the diode at this point, which is V2, is 3 volts. So if this is 3 volts, note that we only focused on D1. So if at one side we have 3 volts and at the anode side we have 10 volts, so we have 10 volts and then we have 3 volts, then the diode should conduct in that case, and the assumption that the diode is off is not valid, because the voltage on there's a higher potential on the anode side, so we expect it to conduct. So the D1 is off, is not valid. Let's test the other assumption, which is D2 is on. Okay, for D2 to be on, one thing that we have to note is that a positive current should actually flow through it. So if you assume that there is such a current, and this current is in fact 3 divided by 6 kilo ohms, which is about 0.5. So positive current flows through such a case, and all data indicates that this is in the forward bias region, because we apply a positive current and then a positive voltage at 3 volts. So if you simply consider this part of the circuit, that's in the forward bias region, and the diode should conduct. So the fact that D2 is on is a valid statement, but D1 is off is not a valid statement. Since these two statements are connected by AND, the net result of this case is not a correct statement. Okay. The last part, D1 is on and D2 is on. I think I can leave this as an exercise to you. But to answer this question, I think you might need Kirchhoff's voltage laws to find those two currents, I1 and I2, because both currents in this case are on. So in this case, since we've actually found the correct statement, which is D1 is on and D2 is off, we might as well stop at this point, but You can continue to this point, and then you will also continue to the next point. Okay, so this is typical case of diodes. Maybe let's go back where we started. Okay, assume diodes are ideal, find the state of these diodes. Maybe another way to alter such a question is, instead of assuming that the diodes is ideal, what if one assumes that the diodes are not ideal? They can be modeled as an offset diode model. Let's say the threshold voltage is 1 volts. So what happens in that case? Okay, maybe then I can leave that also as an exercise, which is to find the state of the diodes if for the case that the diodes are not ideal but threshold voltage is 1 volt.